The universe is actively breaking its own rules. Albert Einstein once said the most incomprehensible thing about the universe is that it is comprehensible, yet modern discoveries constantly challenge that very idea. This journey through 25 space revelations will completely reshape your understanding of reality itself. You will see the cosmos not as a silent void, but as a dynamic and deeply mysterious entity. We will explore how the very fabric of space can ripple, why most of the universe is made of stuff we cannot see, and how time itself can warp and bend. By the end, you will look up at the night sky and perceive an entirely different cosmos. How much of what we consider fundamental truth is actually waiting to be rewritten. Einstein's spacetime pond was not just rippling, it was ringing. For nearly a century, his prediction of gravitational waves existed as a ghost in the machine of physics, a beautiful mathematical consequence of his theory that even he doubted we would ever physically sense. The problem was one of scale. A gravitational wave passing through Earth would distort the entire planet by less than the width of an atom. Detecting such an infinitesimal shiver seemed almost fantastical. Then, in 2015, an instrument of almost unimaginable precision called LIGO did the impossible. It heard the chirp. That sound was the death spiral of two black holes, each about 30 times the mass of our Sun, colliding over 1 billion light-years away. In their final fraction of a second, they converted a mass 3 times that of our Sun into pure energy, vibrating the fabric of the cosmos itself. This was not a discovery seen through a telescope, it was one heard with a new kind of ear. It confirmed that space is not a static stage where events simply play out. It is an active participant, a dynamic material that can be stretched and squeezed, carrying the echoes of the most violent events across the universe. This new sense of hearing fundamentally changed our perception of reality. It proved we could observe the invisible, listening to the silent symphony of colliding black holes and neutron stars. And if spacetime itself can ripple, then what else can it do? It can, quite literally, bend the very light that travels through it. That ringing fabric of spacetime does more than transmit waves, it warps the very path of light itself. Think of a ray of light from a distant star, not as an invincible laser beam, but as a traveler forced to follow the curves in the road, a road bent by gravity. This is gravitational lensing, a phenomenon where a massive object, like a galaxy cluster, acts as a cosmic magnifying glass. It was one of the most dramatic predictions of Einstein's theory of general relativity, suggesting that gravity was not just a force between objects, but a curvature of space and time that even light had to obey. The proof came in 1919 during a total solar eclipse. The astronomer Arthur Eddington led an expedition to measure the positions of stars visible near the darkened sun. He found their light was not where it should have been. The sun's gravity had subtly bent the starlight, shifting its apparent position in the sky. This single observation catapulted Einstein to worldwide fame, proving that our universe operates under rules far stranger than Newton ever envisioned. Today, gravitational lensing is a fundamental tool for astronomers. It allows us to map the invisible, revealing the distribution of dark matter by how its gravity distorts the light from galaxies behind it. It can magnify the most distant objects in the early universe, bringing them into view, and even help us find exoplanets by the tiny telltale warps they create. As NASA astrophysicist Jane Rigby once said, lensing turns the universe into a giant telescope. This profound bending of reality demonstrates that gravity is the ultimate sculptor of our cosmic landscape, not merely attracting matter, but twisting the very canvas upon which reality is painted. And if mass can warp the cosmos so dramatically, what happens when that warping becomes absolute, creating a point of infinite density from which not even light can escape? That ultimate warping of a black hole represents one kind of cosmic destiny, a relentless pull inward. But the universe, it turns out, is dominated by a force that does the exact opposite. The cosmos is not just expanding, it is accelerating. This discovery was so shocking it completely upended our vision of the universe's fate. For decades, the prevailing idea was that after the Big Bang, the mutual gravity of all the matter in the cosmos was acting like a cosmic brake, gradually slowing the expansion. The great question was whether that brake was strong enough to one day pull everything back in a big crunch, or if the universe would just coast onward forever. In the late 1990s, two teams of astronomers set out to measure this deceleration by observing incredibly distant stellar explosions known as Type 1, a supernova. These supernovae are what scientists call standard candles, meaning they always explode with the same intrinsic brightness. By measuring how bright they appear from Earth, astronomers can calculate their precise distance. And by analyzing the light from these explosions, they can determine how much the universe has stretched since that light began its journey billions of years ago. The results were not just surprising, they were paradigm-shattering. The distant supernovae were fainter than they should have been. This meant they were farther away than anyone had predicted. The only possible explanation was that the expansion of the universe was not slowing down at all. It was speeding up. Some unknown repulsive force, counteracting the pull of gravity, was pushing galaxies apart faster and faster. This mysterious force was given a name, dark energy. The discovery was so profound it earned the teams the Nobel Prize in Physics in 2011. As team leader Saul Perlmutter described it, it was like learning the universe has a secret engine. We now believe dark energy makes up about 68% of everything in the cosmos. It is the dominant component of the universe, and we have almost no idea what it is. It could be a property of empty space itself, a constant energy density woven into the vacuum, or it could point toward a modification of Einstein's theory of gravity on the largest scales. This single finding rewrote the ultimate fate of the cosmos. Instead of a big crunch or a gradual coasting, we now foresee a cold, lonely end, where galaxies accelerate away from one another until each island universe is isolated in an ever-expanding, fading darkness. But if this mysterious energy is pushing everything apart, what is it pushing against? What is the cosmic fabric, the immense scaffolding, that holds the universe together in the face of this relentless expansion? The same cosmic fabric that dark energy stretches is simultaneously held together by an invisible scaffold. Galaxies spin at velocities that should tear them apart, flinging stars into the void like water from a spinning wheel. Yet they remain intact, bound by the grip of something we cannot see. This is the profound mystery of dark matter. The first clues emerged in the 1930s with a brilliant and often contentious astronomer, Fritz Zwicky. While studying the Coma Cluster, a vast collection of galaxies, he made a startling calculation. The individual galaxies were moving so quickly that the combined gravity of all the visible stars and gas should be entirely insufficient to hold the cluster together. It should have flown apart eons ago. Zwicky proposed the existence of Dunkel Materie, or dark matter, an unseen substance whose gravitational pull was the only thing keeping the cluster intact. For decades, his idea was largely ignored. Then, in the 1970s, astronomer Vera Rubin provided irrefutable evidence. By meticulously measuring the rotation speeds of stars within spiral galaxies, she found something that defied Newtonian physics. Stars far from the galactic center, in the sparse outer regions, were orbiting just as fast as those near the bright core. According to the laws of gravity, these distant stars should have been slowing down like planets in our own solar system. The only explanation was that each galaxy was embedded within a massive, invisible halo of matter, a halo extending far beyond the visible edge of the stars. This dark matter does not interact with light at all. It does not shine, absorb, or reflect. We cannot see it, but we can feel its gravitational embrace everywhere. Its presence is confirmed by the way it bends light through gravitational lensing, and its imprint is frozen into the patterns of the cosmic microwave background, the afterglow of the Big Bang. We now know this mysterious substance makes up about 27% of the universe, far outweighing all the ordinary matter that makes up stars, planets, and us. So what is it? The best guesses range from weakly interacting massive particles, or WIMP, hypothetical heavy particles that barely interact with normal matter, to actions, incredibly light particles flowing through the cosmos like an invisible sea. Its true nature remains one of the greatest puzzles in physics, a ghostly presence that forces us to question what the universe is really made of. This invisible architecture not only holds galaxies together, but it also provided the essential gravitational seeds for them to form in the first place. Without dark matter, the cosmos would be a dark and formless void. So if this unseen scaffold dictated the large-scale structure of everything, what was the original blueprint? What was the primordial seed from which this entire cosmic tapestry grew? That invisible cosmic scaffold, the dark matter that gave the universe its structure, needed a blueprint, a starting point from which to grow. That blueprint was delivered to us not as a detailed drawing, but as a faint, cold whisper from the dawn of time. In 1965, two radio astronomers named Arno Penzias and Robert Wilson were working with a massive, ultrasensitive horn antenna in New Jersey. Their goal was to study radio waves from our own galaxy, but they were plagued by a persistent, maddening noise. It was a uniform hiss, a static that came from every direction in the sky, day and night, and they could not get rid of it. They scrubbed the antenna clean, even evicting a pair of pigeons they suspected were leaving a conductive white material behind, but the noise remained. This was not a technical flaw. It was the oldest light in the universe. They had accidentally stumbled upon the cosmic microwave background, the cooled and stretched remnant of the universe's fiery birth. This all-sky glow is the afterglow of the Big Bang itself, a snapshot from a time when the cosmos was just 380,000 years old. Before that moment, the universe was a hot, dense plasma, a searing fog where light was constantly scattered by free electrons, unable to travel in a straight line. As the universe expanded and cooled, electrons and protons combined to form the first neutral atoms, and suddenly the fog cleared. That first flash of light, once blindingly bright and energetic, has been traveling for over 13 billion years, stretched by the expansion of space into the microwave part of the spectrum, now just a few degrees above absolute zero. This discovery earned Penzias and Wilson the Nobel Prize, providing the smoking gun evidence for the Big Bang theory. But the story did not end there. Later satellites like COBE, WMAP, and Planck mapped this background radiation with exquisite precision. They found it was not perfectly smooth. Embedded within it are tiny fluctuations, minute variations in temperature, mere millionths of a degree. These are the cosmic seeds. These tiny ripples in density are the gravitational blueprints, the slight overdensities where dark matter began to clump, eventually pulling in normal matter to form the first stars, galaxies, and the vast cosmic web we see today. As cosmologist George Smoot famously described it, seeing this detailed map was like seeing the face of God. The cosmic microwave background confirmed our origin story, and gave us the universe's vital statistics, its age, composition, and geometry. Yet this profound picture also pointed to a problem. The universe was far too uniform, its temperature too consistent across vast distances that could never have been in contact. This cosmic conundrum demanded an even more dramatic beginning, a moment of unimaginable violence that set the stage for everything to come. That faint cosmic whisper from the Big Bang held a profound puzzle within its near-perfect uniformity. How could regions of the universe on opposite sides of the sky have the exact same temperature when, according to the standard Big Bang timeline, there had not been enough time for light or heat to travel between them to even things out? It was like walking into a vast, crowded room and finding every single person holding a perfectly synchronized watch, with no explanation for how they coordinated. This was the horizon problem, and it demanded a radical solution. The answer came in the form of a truly breathtaking idea, cosmic inflation. Proposed in the 1980s by physicist Alan Guth, this theory suggests that in the very first fraction of a second of its existence, the universe underwent a growth spurt of unimaginable ferocity. For a fleeting moment, a trillionth of a trillionth of a trillionth of a second, the cosmos expanded faster than the speed of light. This was not matter moving through space, but space itself stretching at a rate beyond cosmic limits. This inflationary burst solved multiple problems at once. It took a tiny, subatomic patch of the primordial universe that was already in thermal contact and stretched it into a volume larger than our entire observable universe today, explaining the perfect synchronization we see in the cosmic microwave background. It also ironed out any initial curvature, rendering the geometry of our universe flat, just as our most precise measurements confirm. Furthermore, this process would have diluted any exotic relics from the earliest moments, like magnetic monopoles, which theorists predicted should be everywhere, yet we have never found one. The theory made a crucial prediction. This violent stretching would have left an imprint on the cosmos, creating specific, subtle patterns in the density fluctuations of the early universe. When our most powerful space telescopes like Planck mapped the cosmic microwave background, they found exactly those predicted patterns. The statistical fingerprint of inflation was there, etched into the oldest light we can see. The implications of this are staggering. If inflation is true and the evidence is compelling, then the observable universe, with its hundreds of billions of galaxies, is just an infinitesimal bubble in a far vaster, perhaps infinite multiverse. As Alan Guth famously quipped, the universe is the ultimate free lunch, a colossal structure that may have emerged from almost nothing. This explosive beginning did more than just solve cosmic puzzles. It created the initial conditions for everything that followed. It set the stage for gravity to get to work, pulling on those tiny ripples to forge the very first building blocks of existence. Deep within that explosive beginning, a clock was ticking. In the first 3 minutes of the universe, the conditions were so extreme that the entire cosmos acted as a single, colossal nuclear furnace. This was the era of Big Bang Nucleosynthesis, the fleeting moment when the first atomic nuclei were forged from the primordial soup of particles. The temperature and density were just right for protons and neutrons to collide and stick together, but only for a very short window of time. The first crucial step was the formation of deuterium, a heavy isotope of hydrogen. For a brief period, the universe was a delicate balance between the force of the expansion, which was rapidly cooling everything, and the nuclear forces trying to build things up. Protons and neutrons fused into deuterium, and that deuterium then fused into helium. In those frantic first minutes, about a quarter of the universe's ordinary matter by mass was fused into helium-4, the most stable light nucleus. Trace amounts of other elements were also created, like helium-3 and a tiny, tiny sprinkling of lithium. But the process was brutally cut short. The universe expanded and cooled too quickly, shutting down the fusion process before any heavier elements, like carbon or oxygen, could form. Everything else, every atom that makes up our bodies and our world, would have to be made much later inside the hearts of stars. The profound significance of this is in the prediction. In the 1940s, physicists like George Gamow and his team calculated what the abundances of these light elements should be based on the known laws of nuclear physics and the conditions of the early universe. Decades later, when astronomers measured the oldest stars and the most pristine gas clouds in the universe, places untouched by later stellar processes, they found a near-perfect match. The amount of helium, deuterium, and lithium observed in the cosmos is exactly what the Big Bang model predicts. This agreement is not a rough estimate, it is a precise confirmation. As the renowned astrophysicist James Peebles put it, it is a remarkable fact that the simplest model works so well. This primordial alchemy does more than just confirm the hot Big Bang, it also acts as a cosmic probe. The precise ratios of these elements are exquisitely sensitive to conditions in the early universe. They tell us, for instance, how many different types of neutrinos can exist, setting a limit on the fundamental particles of nature. They also provide the most accurate measurement of the total amount of ordinary matter, the atoms and molecules we are made of, in the entire cosmos. And that measurement reveals a stunning truth, that all the stars, galaxies, and planets we can see account for less than 5% of the universe. This foundational process, the forging of the first nuclei, was powered by a flood of enigmatic particles that filled the young cosmos, particles that barely interacted with the building blocks of matter. That first cosmic alchemy, forging hydrogen and helium, was governed by a ghost. The entire process in those initial minutes was exquisitely sensitive to the number and type of particles flooding the universe, and one particle in particular held a crucial key, the neutrino. These are the most elusive, ghostly inhabitants of the subatomic world. Trillions of them are passing through your body every second, as if you were transparent. They barely interact with anything born from nuclear reactions and stellar fires. During Big Bang Nucleosynthesis, neutrinos were not just passive spectators, they were active participants in the cosmic drama. The rate at which protons and neutrons fused depended critically on how fast the universe was expanding and cooling, and that expansion rate was, in turn, dictated by the total energy density of the cosmos, which included the seething sea of these invisible neutrinos. If there were more types of neutrinos, or if they behaved differently, the cosmic clock would have ticked at a different pace. More neutrinos would have made the universe expand faster, shutting down the nuclear furnace sooner. This would have left less time for neutrons to be captured, resulting in significantly less helium being produced. The fact that we observe a universe that is 25% helium by mass, a quarter of all ordinary matter, acts as a precise cosmic neutrino counter. It tells us that the number of light neutrino species must be exactly 3, a prediction made by the Big Bang model that was later spectacularly confirmed in particle accelerator experiments. This perfect agreement is a stunning example of cosmology and particle physics converging. The helium in a child's birthday balloon is not just a remnant of the Big Bang. It is a fossilized relic of a time when the entire universe was as hot as the core of a star, and it carries within it the signature of the most ghostly particles known to science. This primordial element factory, confirmed by the silent work of neutrinos, locked in the basic chemical composition of the cosmos for billions of years. But this simple hydrogen-helium universe was static and dark. It would take a new kind of cosmic forge, a place of immense pressure and heat, to break the deadlock and create the rich chemistry that would eventually lead to us. That ghostly neutrino sea from the universe's first moments held a secret, one that would only reveal itself when we looked at our own sun. For decades, a deep and troubling mystery haunted solar physics. We knew the sun shone through nuclear fusion, a process that should flood space with a specific type of ghostly particle, the electron neutrino. In the 1960s, a physicist named Ray Davis built a revolutionary detector deep underground in the Homestake gold mine. His tank was filled with 615 tons of cleaning fluid, a perchloroethylene designed to catch these elusive solar messengers. The results were baffling. Davis's experiment detected only about 1/3 of the neutrinos that our best models of the sun predicted. Either our understanding of how the sun works was completely wrong, or something very strange was happening to the neutrinos on their journey. This was the solar neutrino problem, and it persisted for over 30 years. The solution was as elegant as it was revolutionary. Neutrinos, it turns out, are not static. They oscillate. As they travel through space, they morph between their three different types or flavors: electron, muon, and tau. Davis's detector was only sensitive to electron neutrinos, the kind the sun produces. By the time those neutrinos had traveled the 93 million miles to Earth, 2/3 of them had changed into muon or tau neutrinos, becoming invisible to his experiment. This incredible transformation was definitively confirmed at the turn of the millennium by two landmark experiments: Japan's Super Kamiokande and Canada's Sudbury Neutrino Observatory, or SNO. The SNO detector, using heavy water, had the unique ability to see all three neutrino flavors at once. When it looked at the sun, it counted the full, predicted number of neutrinos, solving the decades-long puzzle. As Nobel laureate Arthur MacDonald of the SNO team declared, it was a transformation in our understanding. This discovery had a staggering implication. For neutrinos to oscillate, they must have mass, however tiny. This simple fact shattered a core assumption of the standard model of particle physics, which had always treated neutrinos as completely massless. We now know these ghostly particles do have mass, a finding that forces us to look beyond our current theory of the subatomic world. But the implications run even deeper. This shape-shifting property may hold the key to one of the universe's greatest imbalances. Why are we here at all? The Big Bang should have created equal amounts of matter and antimatter, which would have annihilated each other, leaving behind a universe of pure light. Yet we live in a cosmos made entirely of matter. Neutrino oscillations could be a critical piece of this puzzle, a mechanism that favored the survival of matter over antimatter in the universe's first moments. This ghostly transformation connects the heart of our sun to the very reason for our existence. That ghostly transformation of neutrinos connects directly to a cosmic crime scene of unimaginable scale. The universe we see today is built from matter, but the Big Bang should have been perfectly fair, creating equal amounts of matter and its mirror opposite, antimatter. For every particle of matter born, an antiparticle should have emerged. They are perfect twins but with opposite charges. When matter and antimatter meet, they annihilate in a flash of pure energy. So why did this not happen? If the cosmos had started with perfect balance, every particle would have found its antiparticle, and the entire universe would have vanished into a brief, brilliant flash of light, leaving behind an empty, dark expanse. The fact that we are here, that stars and planets exist, is proof that this perfect symmetry was broken. A tiny, almost imperceptible bias for matter over antimatter must have existed in the laws of physics themselves. This is the mystery of baryogenesis, the genesis of the stuff we are made from. The first clue that such a bias was even possible came in 1964. Physicists James Cronin and Val Fitch were studying the decay of strange particles called kaons and their antimatter counterparts, antikaons. They discovered something that shocked the physics world. The decays were not perfectly identical. There was a slight but definite difference in how the particles and antiparticles behaved. This was a violation of CP symmetry, a fundamental principle that assumed the laws of physics would be the same if you swapped a particle with its antiparticle and viewed its mirror image. This discovery, which earned them the Nobel Prize, proved that nature has a tiny built-in preference. Yet, when physicists calculated the magnitude of this preference, it was far too small. The CP violation seen in the lab could only account for a universe with 1,000,000,001 matter particles for every billion antimatter particles. After the annihilation, that would leave behind just a single particle per billion. But to create the universe we see, the imbalance had to be much, much larger. The known effects are insufficient by a factor of about 10 billion. So where did this overwhelming preference for matter come from? This points directly to new physics, to processes and particles we have not yet discovered. One compelling theory is leptogenesis, which suggests that the very neutrinos we just discussed, with their tiny mass and ability to oscillate, could have been the key actors. In the searing heat of the early universe, heavy, hypothetical neutrinos may have decayed in a way that subtly produced more matter than antimatter. This initial bias in the lepton family could then have been transferred across the cosmos to create the matter dominance we see in baryons, the protons and neutrons that make up our world. As the physicist Andrei Sakharov first outlined, creating a matter-dominated universe required three specific conditions: a universe out of thermal equilibrium, processes that violate CP symmetry, and interactions that violate the conservation of baryon number. The search is now on to find the processes that satisfied these conditions with enough force to build a cosmos. This fundamental asymmetry is not just a historical curiosity, it is the reason anything complex exists at all. And to understand the extreme environments where such symmetries are shattered, we must look to the most violent events in the present-day universe, where matter is pushed to its absolute limits. Those extreme cosmic forges where matter vanishes forever are not the perfect traps we once believed. Stephen Hawking performed a breathtaking act of theoretical magic in 1974, proving that black holes are not completely black. They glow, and in doing so, they slowly evaporate into nothingness. This Hawking radiation emerges from the violent marriage of two great but incompatible theories: Einstein's general relativity and the bizarre world of quantum mechanics. At the very edge of a black hole, right at the precipice of the event horizon, the fabric of spacetime is churned into a quantum froth. Here, pairs of virtual particles constantly flicker in and out of existence, borrowing energy from the vacuum for an impossibly brief moment. Usually, these particle pairs annihilate each other almost instantly, paying back their energy debt. But at the event horizon, a cosmic theft can occur. One particle of the pair falls into the black hole's bottomless gravity, while its partner is left stranded outside, suddenly real. With its debt unpaid, this escaped particle steals a tiny amount of the black hole's mass energy and radiates away into space. From our perspective, the black hole has just emitted a particle. This process is incredibly slow for a typical stellar black hole, taking far longer than the current age of the universe to have any noticeable effect. But for tiny, primordial black holes that might have formed in the early cosmos, this evaporation would be a spectacular finale, ending in a violent burst of gamma rays. Hawking's calculation revealed something even more profound. If a black hole emits radiation, then it must have a temperature, and if it has a temperature, it has entropy, a measure of disorder. This forged an unexpected and deep connection between the laws of thermodynamics, which govern heat and energy, and the laws of gravity that describe space-time itself. As Hawking himself quipped with characteristic wit, black holes ain't as black as they are painted. Yet this brilliant insight created one of the most persistent paradoxes in modern physics. The radiation that escapes appears to be completely random, a featureless thermal hiss carrying no information about the specific stars, planets, or atoms that fell in. According to quantum mechanics, information can never be truly destroyed, but according to Hawking's original math, it seems to be irretrievably lost down the black hole, vanishing when the black hole itself evaporates. This information loss paradox pits quantum theory against general relativity in a fundamental way, suggesting our understanding of either gravity or quantum physics or both is deeply incomplete. The slow quantum glow of a black hole is a whisper from the edge of physics, a sign that the greatest unification of all is still waiting to be found. That slow quantum glow from a black hole's edge hints at a deeper, stranger connection woven into the fabric of reality itself. Imagine two particles born from the same event, then flung to opposite sides of the galaxy. According to the bizarre rules of quantum mechanics, they remain linked in an intimate dance. Measure the spin or polarization of one, and its distant partner instantly assumes a corresponding state, as if they share a single existence. Albert Einstein found this idea so unsettling he derided it as spooky action at a distance, convinced it revealed a flaw in the theory, not a feature of the universe. He believed there must be some hidden local mechanism, some unseen variable directing the particle's behavior. For decades, it remained a philosophical debate. Then, in the 1980s, physicist Alain Aspect performed a series of elegant experiments that settled the issue. By measuring entangled particles in rapidly switching detectors, he closed potential loopholes. The results were definitive. The particles were communicating their states faster than light could travel between them, not through any signal we understand, but through a fundamental, non-local connection. This was not a failure of the theory, but a breathtaking feature of our world. John Bell had provided the mathematical framework years earlier, his inequalities creating a test that local hidden variable theories would fail. The universe, it seems, chose spookiness. The implications ripple outward from the lab to the cosmos itself. How did the entire universe achieve such a uniform temperature, as seen in the cosmic microwave background, if distant regions were never in contact? Perhaps the answer lies in quantum entanglement. In its earliest moments, every particle may have been entangled with every other, creating a unified whole that stretched across space during inflation. This primordial entanglement could be the reason the cosmos looks so similar in all directions. Some physicists like Juan Maldacena and Leonard Susskind take this idea even further. They propose that the very fabric of space and time, the stage upon which the cosmos plays out, might be an emergent phenomenon. What we perceive as empty space could be a vast, intricate network of entangled quantum bits. The connection between two entangled particles might literally be stitching space-time itself into existence. This challenges our most fundamental notions of reality and locality. Information seems to be transferred instantaneously, appearing to violate the cosmic speed limit set by light. Yet, crucially, we cannot use this to send a meaningful message faster than light. The correlation is instantaneous, but the outcome is random, preventing us from building a superluminal telegraph. This non-local reality is not just a microscopic curiosity. It is vital for understanding black holes and the quest for a theory of quantum gravity. Inside a black hole where gravity becomes infinite, perhaps the very concept of locality breaks down entirely, replaced by a web of quantum connections. The universe, it seems, is not a collection of separate objects in a void, but a single, deeply interconnected quantum system. If the vacuum of space itself is a seething, entangled ocean, what other cosmic secrets might be hidden within its apparent stillness? That interconnected quantum ocean of empty space is not a placid void, but a seething, energetic sea. You can witness its power with a simple yet profound experiment. Take two perfectly smooth, uncharged metal plates and place them parallel to each other in a perfect vacuum, separated by a tiny gap. According to classical physics, nothing should happen. Yet they will inevitably pull together, as if drawn by an invisible force. This is the Casimir Effect, a phenomenon predicted by Dutch physicist Hendrik Casimir in 1948. The force arises from the restless nature of the quantum vacuum. Empty space is not truly empty. It is a turbulent foam where virtual particle pairs constantly flicker into existence, borrowing energy from the universe for a fleeting moment before annihilating each other. These are not mere mathematical abstractions. They exert a real physical pressure. Think of the vacuum outside the plates as a choppy ocean with waves of all possible sizes. But in the narrow gap between the plates, only certain wavelengths of virtual photons, the carriers of the electromagnetic force, can fit, much like how only specific musical notes can resonate in a flute. This restriction means there are fewer possible virtual particles between the plates than outside them. With more virtual particles bombarding the outer surfaces, the net result is an inward push, forcing the plates together. For decades, this was a theoretical curiosity. Then, in the 1990s, physicist Stephen Lamoureux performed a landmark experiment, measuring this minuscule force with exquisite precision. He confirmed that the vacuum does indeed push, just as Casimir had foreseen. This tangible force provides some of the most direct evidence we have for zero-point energy, the idea that even at absolute zero, the lowest possible energy state, space itself still buzzes with activity. This energy inherent in nothingness is not just a laboratory oddity, it has cosmic implications. Many physicists believe that the same kind of quantum fluctuations that create the Casimir force are what drove the inflationary burst at the beginning of the universe, stretching a quantum speck into a cosmic landscape. Furthermore, this vacuum energy is the leading candidate for the mysterious dark energy that is accelerating the expansion of the cosmos. The cosmological constant, a term Einstein once inserted and later called his greatest blunder, may in fact be this energy of the vacuum, a constant repulsion woven into the fabric of space itself. The gentle pull between two metal plates in a lab connects directly to the ultimate fate of the entire universe, a force born from the restless churn of nothing at all. That gentle push between metal plates is a whisper of a far greater force residing within the void itself. Einstein first grappled with this idea when he tried to describe a static, unchanging universe with his equations of general relativity. He found his math demanded the cosmos should be either collapsing under its own gravity or flying apart. To force a standstill, he introduced a fudge factor, a repulsive term he called the Cosmological Constant. It represented a latent energy intrinsic to the fabric of empty space, a pressure pushing outward to precisely balance gravity's inward pull. When Edwin Hubble later discovered the universe was not static at all, but expanding, Einstein famously discarded this idea, calling it his greatest blunder. Yet the cosmic joke was on him. Decades later, the discovery of the accelerating universe revealed that a repulsive force, something eerily similar to his cosmological constant, is not only real but dominates the cosmos. This energy of the vacuum, the same seething quantum activity that creates the Casimir Effect, appears to be the engine of cosmic acceleration, a constant repulsion woven into the nothingness between galaxies. But here lies the most profound embarrassment in all of modern physics. When theorists calculate how much energy this quantum vacuum should contain, the number is catastrophically wrong. They add up all the possible fluctuations of every quantum field, and the result is an energy density so immense it should have ripped the universe apart in its first instant of existence. The theoretical prediction is larger than the observed value by a factor of 1 followed by 120 zeros. It is the worst mismatch between theory and experiment in the history of science. As physicist Sean Carroll bluntly stated, the vacuum energy is the most embarrassing number in physics. This colossal failure is known as the cosmological constant problem. It suggests a deep flaw in our understanding, a fundamental disconnect between the world of the very small, governed by quantum mechanics, and the world of the very large, described by general relativity. Perhaps we are missing a crucial piece of the puzzle, a symmetry or a cancellation mechanism that brings the vacuum's ferocious energy down to the whisper we observe. This glaring tension forces physicists to consider radical alternatives. Maybe Einstein's theory of gravity itself is incomplete on the largest scales. Modified gravity theories, like those proposed by Mordechai Milgrom, suggest that gravity behaves differently when it becomes incredibly weak in the vast emptiness between galaxy clusters, creating the illusion of dark energy without needing a mysterious vacuum force. The cosmological constant, once dismissed as a blunder, now stands as a monumental challenge, a beacon pointing toward the next great revolution in physics, where the quantum world and the cosmic stage must finally be reconciled. If the vacuum of space itself is not what we think, then where else might our assumptions about reality be leading us astray? Even the most carefully planned journeys can reveal a hidden tug from the unknown. As the Pioneer 10 and 11 spacecraft sailed beyond the orbits of the planets, becoming humanity's first emissaries to the void between stars, they carried with them a tiny, stubborn mystery. By the 1990s, as they were billions of miles from Earth, radio tracking data revealed something deeply puzzling. Both probes were experiencing a minuscule but constant acceleration back toward the Sun, a slight but persistent drag on their escape from the solar system. It was as if a ghostly hand was gently applying the brakes. This was the Pioneer Anomaly, a deviation so small it amounted to less than a billionth of the gravity we feel on Earth, yet it defied all conventional explanations for over a decade. The possibilities scientists considered were tantalizing. Was it the gravitational pull of unseen dark matter clustered in our solar system? Could it be a subtle flaw in our understanding of gravity itself, a hint that Einstein's general relativity needed a tweak at the vast scales of interplanetary space? Or was the answer something far more mundane, yet incredibly difficult to model? The resolution required a monumental effort in forensic spacecraft archaeology. A team led by Slava Turyshev spent years recovering old data tapes and painstakingly modeling every conceivable force acting on the distant probes. They concluded the primary culprit was heat. Not an external force, but the spacecraft's own warmth. The plutonium in their power sources generated heat that was radiated away into space. Crucially, this thermal radiation was not perfectly even. More heat was emitted from the back of the spacecraft, the side facing away from the Sun, than from the front. This created a tiny net push, like a very faint photon rocket, slowing the probes down just enough to account for most of the anomalous acceleration. It was a triumph of meticulous engineering analysis. Yet, as Turyshev himself noted, the experience taught us to be humbler. even after accounting for the thermal push, a tiny sliver of the anomaly, a minuscule fraction, remained unexplained. This lingering whisper reminds us that our most precise instruments are now sensitive enough to detect effects we have not fully considered. The Pioneer Anomaly stands as a powerful lesson that the universe often speaks in murmurs, not shouts, and that the path to discovery sometimes lies in chasing down the most elusive of errors. This relentless pursuit of precision in our own cosmic backyard forces us to question the very laws we take for granted, pushing us to test gravity itself in ways Einstein could never have imagined. The ghostly tug on the Pioneer probes was a whisper, but some scientists hear a far louder cry for a rewrite of the laws of gravity itself. For decades, the dominant explanation for galaxy rotation and cosmic structure has been dark matter, an invisible substance whose gravity holds everything together. But what if we are not missing matter but misunderstanding gravity? This is the radical proposition of modified Newtonian dynamics, or MOND, proposed by physicist Mordechai Milgrom in 1983. MOND suggests a breathtakingly simple alternative. Instead of invoking vast halos of unseen dark matter to explain why stars at the edges of galaxies orbit so quickly, Milgrom proposed that gravity simply behaves differently when it becomes incredibly weak. In the sparse outskirts of a galaxy, where the gravitational acceleration drops below a certain tiny threshold, the force of gravity switches from the familiar inverse square law to a new regime. It is like discovering that water, when it gets very, very cold, does not just get colder, it turns to ice. This single change, this modification to Newton's second law at ultra-low accelerations, makes a stunning prediction. It says that if you know how much ordinary, visible matter is in a galaxy, you can precisely predict the rotation speed of its stars, and for decades, across hundreds of galaxies, this is exactly what MOND has done, matching the observed rotation curves with remarkable accuracy without a single particle of dark matter. As astronomer Stacy McGaw, a leading advocate for testing these ideas, often states, the data demand we keep an open mind. Yet for all its elegance on the scale of individual galaxies, MOND faces its own profound challenges. It struggles to explain the gravitational dynamics of entire clusters of galaxies, where the observed gravity is far stronger than the modified law predicts. It also fails to naturally account for the detailed patterns in the cosmic microwave background, the primordial blueprint of the universe, which dark matter models reproduce with stunning precision. The debate is far from settled, pushing scientists to devise ever more precise tests. Recent observations of wide binary star systems, pairs of stars orbiting each other at great distances where MOND effect should kick in, are providing a new cosmic laboratory. The initial results are ambiguous, keeping both camps in suspense. This is not merely a technical argument. It is a battle over the fundamental nature of reality. Is the cosmos filled with a mysterious, invisible substance we have yet to identify? Or are the laws of gravity themselves an illusion that breaks down in the deepest quiet of space? MOND represents a courageous alternative, a reminder that even our most cherished theories must be tested to their limits. To find the answer, we must venture beyond modifications and into environments where gravity is not just modified, but completely shattered. Our own planet is constantly twisting the fabric of reality around it. As the Earth spins, it does not simply rotate within a static arena of space. It pulls the very fabric of space-time along for the ride. This subtle effect is known as frame dragging, the cosmic equivalent of a spoon slowly stirring a vast vat of honey. The mass and rotation of any object will distort the spacetime around it, and Einstein's equations predicted this over a century ago. But detecting this minute twist from our relatively small planet was an engineering challenge of almost absurd precision. To prove it was happening, scientists devised one of the most exquisite experiments in history, the Gravity Probe B mission. Launched in 2004, this satellite carried 4 of the most perfect spheres ever created, gyroscopes the size of ping-pong balls, polished to within a few atoms of perfect roundness. These spheres were chilled to near absolute zero and placed in a polar orbit around Earth. Their spin axes initially pointed toward a distant guide star, IM Pegasi. If spacetime was truly static, these gyroscopes would have remained pointed in that same direction forever. But if Einstein was right, the gentle tug of the Earth's rotation would slowly twist the gyroscope's alignment over time. The effect they were trying to measure was vanishingly small, a drift angle of just 1 degree every 100,000 years. After more than a year of collecting data, the team announced their result. The gyroscopes had drifted. The fabric of spacetime was indeed being dragged around our planet, just as general relativity foretold. Independent data from the LEGIO's satellites, which used laser ranging to track their orbits, further confirmed the finding. While the effect on Earth is subtle, around a rapidly spinning black hole, frame dragging becomes a cosmic maelstrom. The rotation is so violent it creates a region outside the event horizon called the ergosphere, where spacetime itself is dragged around at nearly the speed of light. Within this region, nothing, not even light, can remain stationary. It is a place where the very concept of standing still loses all meaning. This profound connection between rotation and spacetime is not just a curiosity. It is a fundamental engine for the most energetic phenomena in the universe. The intense frame dragging around supermassive black holes is believed to power the colossal jets of matter and energy that scream across thousands of light years, shaping entire galaxies in their wake. That same frame dragging effect that gently twists spacetime around our Earth becomes a cosmic hurricane around a supermassive black hole. Here, the twisting is so violent it forges the most powerful engines in the known universe, relativistic jets. These are colossal geysers of superheated plasma, screaming out from the poles of a black hole at nearly the speed of light, often stretching for thousands of light years into the intergalactic void. To grasp their scale, imagine a thin beam of energy erupting from the center of our Milky Way, so long it would reach a dozen galaxies away. These jets are the hallmark of active galactic nuclei, the intensely bright hearts of galaxies where a black hole is actively feeding. The power source is a cosmic dynamo of almost unimaginable efficiency. As matter spirals inward in a vast, flat accretion disk, it heats to millions of degrees, glowing brilliantly. But not all of this doomed material falls in. The black hole's insane rotation, its frame-dragging effect, and its immensely powerful magnetic fields work in concert. Think of the magnetic fields as being frozen into the swirling plasma, like strands of thread stirred in honey. The black hole's spin grabs these magnetic field lines and twists them into a tight, powerful coil along its rotation axis. This creates a slingshot, a narrow channel that funnels a fraction of the infalling matter and blasts it outward, focusing its energy into 2 opposing beams. This process converts gravitational energy into focused radiation and particle beams with an efficiency that dwarfs nuclear fusion. As astrophysicist Heino Falk observed, these jets are the universe's particle accelerators, far more powerful than anything we could ever build on Earth. They are so energetic that we can detect them from billions of light years away, often outshining the combined light of every star in their host galaxy. The impact of these jets reverberates across cosmic time. When they plow into the sparse gas between galaxies, They create colossal shock waves that can either trigger the birth of new stars by compressing gas clouds or snuff out star formation by violently heating the galactic fuel. They act as cosmic regulators, pumping immense energy and heavy elements forged in their fires into the intergalactic medium, seeding future generations of stars and planets. Observations from space telescopes like Chandra, which sees X-rays, and Hubble, which sees visible light, have mapped the intricate structure of these jets, revealing knots of intense energy and vast lobes of radio emission where the jets finally slam to a halt. These cosmic geysers demonstrate that black holes are not just passive destroyers, they are active, dynamic architects shaping the evolution of galaxies on a grand scale. If a single black hole can unleash such fury, what happens when two of them collide in a cataclysm that shakes the very cosmos? The birth cry of a black hole is a gamma-ray scream. For a few fleeting seconds, a gamma-ray burst can outshine every star in the observable universe, releasing more energy than our Sun will emit across its entire 10-billion-year lifetime. These cosmic cataclysms were first detected by accident in the 1960s by American Vela satellites, which were designed to monitor for secret nuclear weapons tests. Instead, they found explosions of unimaginable power coming from deep space, not from Earth. For decades, their origin was one of astronomy's greatest mysteries. We now know these bursts come in two distinct flavors, each with a different, violent origin. Long-duration bursts lasting from 2 seconds to several minutes are the death throes of the most massive stars in the universe. When such a star exhausts its nuclear fuel, its core collapses directly into a black hole. The star's outer layers plummet inward, but a fraction of that material is channeled by intense magnetic fields and blasted outward in two narrow, oppositely directed jets. If one of those jets is pointed at Earth, we see it as a brilliant gamma-ray burst. The shorter bursts, lasting less than 2 seconds, have an even more spectacular source. They are the final farewell of two neutron stars spiraling together. These ultra-dense corpses of dead stars circle each other in a deadly dance, rippling space-time until they finally collide and merge, often creating a new black hole in a flash of energy. The definitive proof came in 2017. The LIGO and Virgo observatories detected the gravitational wave chirp of two neutron stars merging. Just 2 seconds later, satellites detected a short gamma-ray burst from the exact same patch of sky. This event, known as GRB 170817A, was a watershed moment. For the first time, we had witnessed the same cosmic event through both gravitational waves and light, opening a completely new window onto the universe. As the late NASA astrophysicist Neil Gehrels so poetically put it, these bursts are the birth cries of black holes. They act as cosmic lighthouses, their brilliant flashes allowing us to probe the composition and geometry of the early universe, testing the laws of physics under conditions of extreme energy and gravity that we could never hope to replicate. And in the wake of these shattering explosions, especially from the merger of neutron stars, they forge and fling into the void the very elements that make life possible. The death shriek of a gamma-ray burst marks the birth of a black hole, but sometimes the stellar corpse left behind is a different kind of marvel. A neutron star is what remains when a star too massive to become a white dwarf, yet not quite massive enough to form a black hole, collapses under its own immense gravity. The entire mass of a star larger than our Sun is crushed into a perfect sphere no wider than a city. The density is beyond human comprehension. A single teaspoon of this material would weigh billions of tons, a mountain compressed into a sugar cube. Theorized in the 1930s, these objects seemed almost too extreme to be real. Then, in 1967, a young graduate student named Jocelyn Bell Burnell was analyzing data from a radio telescope she had helped build. She noticed a curious, repeating signal, a precise pulse of radio waves arriving every 1.337 seconds. It was so regular it seemed artificial, leading her and her team to briefly entertain the idea it might be a sign of extraterrestrial intelligence. They even jokingly labeled it LGM-1 for little green men, but soon more of these pulsars were found. The truth was both natural and astonishing. A pulsar is a rapidly spinning neutron star, a cosmic lighthouse. Its powerful magnetic fields funnel radiation into narrow beams that sweep through space like the beam of a lighthouse. If that beam crosses Earth's path, we observe a pulse with every rotation. The discovery was a total surprise, as Bell Burnell later recalled, a humbling reminder that the universe is full of wonders we have not yet dreamed of. These objects are more than just curiosities, they are unparalleled laboratories for fundamental physics. The matter inside a neutron star is squeezed to such an extreme that atoms cease to exist. Electrons are crushed into protons, forming a solid sphere of neutrons, a single, city-sized atomic nucleus. Under this pressure, the neutrons may dissolve into a soup of even more fundamental particles called quarks, creating states of matter that cannot be replicated anywhere on Earth. The incredible regularity of their pulses makes pulsars the most precise clocks in the galaxy. Astronomers use them to test Einstein's theory of general relativity with exquisite accuracy. The first indirect evidence for gravitational waves came from observing a binary pulsar system discovered by Russell Hulse and Joseph Taylor. They measured how the orbits of these two neutron stars were slowly decaying, exactly as predicted if they were losing energy by rippling spacetime itself, a discovery that earned them the Nobel Prize. We now use networks of pulsars across the galaxy as a gravitational wave detector, listening for the low-frequency hum of merging supermassive black holes. Their precision even makes them ideal for a future interstellar GPS, a navigation system for spacecraft traveling between the stars. A neutron star represents the ultimate triumph of nuclear forces against gravity, a stable configuration at the very edge of oblivion. But if just a little more mass falls onto its surface, that delicate balance shatters and gravity wins its final victory, collapsing everything into a singularity. That point of no return is no longer just a theoretical boundary. For the first time in human history, we have looked directly into the abyss and seen its silhouette. The Event Horizon Telescope collaboration did not just detect a black hole, it took its portrait. The target was the supermassive giant at the heart of the galaxy Messier 87, a behemoth weighing in at 6.5 billion times the mass of our Sun. The resulting image, unveiled in 2019, was instantly iconic, a fiery golden ring of light encircling a perfect circle of darkness. This was the black hole's shadow, the absence of light caused by the event horizon's gravitational grip. The bright ring is not the event horizon itself, but the intense glow of superheated gas being whipped around the black hole at nearly the speed of light, its light bent into a perfect circle by the immense gravitational lensing. The dark heart is the point where those light paths vanish, swallowed forever. This single picture was a monumental confirmation of Einstein's general relativity under the most extreme conditions imaginable. The size and shape of that shadow matched the predictions of his century-old equations with stunning precision. From it, astronomers could not only measure the black hole's colossal mass, but also deduce that it is spinning, a rotating dynamo powering those colossal jets we see screaming across space. To achieve this seemingly impossible feat required turning the entire Earth into a single, planet-sized telescope. The Event Horizon Telescope is not one instrument, but a global network of radio observatories synchronized by atomic clocks. Using a technique called very long baseline interferometry, these widely separated telescopes observed the black hole in unison, their combined data creating a virtual lens as wide as our planet. The resolution was so unimaginably sharp it could, in principle, spot a donut on the surface of the moon. As project director Shepard Doleman declared, they had seen what was thought to be unseeable. This first glimpse past the point of no return does more than confirm a theory. It opens a new era of exploration. We are now peering at the edge of a singularity, a place where the known laws of physics break down. What happens when matter crosses that final threshold? Does it truly vanish, or is information somehow preserved? The black hole's shadow is not an end, but a gateway, challenging us to peer even deeper into the heart of gravity's ultimate mystery. That shadow we have seen is not a silent boundary, but the edge of a profound paradox. Picture throwing a complete encyclopedia into a black hole. It contains every fact, every story, a universe of information. According to Hawking's original calculation, as the black hole slowly evaporates through its thermal radiation, that information seems to be utterly lost, erased from reality. This is the black hole information paradox, and it represents a crisis in physics. Quantum mechanics, the rulebook for the small, states with absolute certainty that information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must always be preserved, a principle known as unitarity. Hawking's work suggested that black holes were the ultimate shredders, violating this most sacred quantum law. For decades, this paradox forced physicists to choose sides, pitting Einstein's general relativity against quantum theory in a fundamental showdown. How could both be correct if one allows for the permanent deletion of information? The search for a solution has led to some of the most mind-bending ideas in modern science. One compelling answer is the holographic principle, championed by physicists like Leonard Susskind. He argues that the universe might be a hologram. In this view, all the information that falls into a three-dimensional black hole is not lost inside, but is perfectly encoded and preserved on its two-dimensional event horizon, the surface that we see as the black hole's shadow. The event horizon becomes a vast cosmic hard drive, storing a pixelated record of everything that has ever fallen in. The three-dimensional world we experience inside could be a projection from that encoded two-dimensional surface. This is not science fiction. The mathematics suggests it is a real possibility. But another, more violent solution has emerged, the firewall hypothesis. If information must be preserved and is encoded on the horizon, then the vacuum around the black hole cannot be smooth and empty as Einstein's equations predict. Instead, the act of encoding that information might require a dramatic break, a wall of unimaginably high energy particles right at the event horizon. Crossing the horizon would not be a gentle passage, it would be an instantaneous incineration. An object would not slowly stretch into spaghetti. It would be vaporized by a firewall the moment it tried to enter, its information instantly smeared onto the surface. This solves the paradox by destroying the infalling object to preserve its data, but it blatantly violates the principle of equivalence, a cornerstone of general relativity which states that free falling through an event horizon should be an unremarkable local experience. So we are left with a stark choice. Does information live on a holographic screen, or is the horizon a wall of fire? As Leonard Susskind famously stated, the universe may indeed be a hologram. This is not merely a philosophical debate about black holes. It is a direct path to a theory of quantum gravity. The way information behaves at this boundary holds the key to unifying the large and the small, the force of gravity with the quantum world. If information is preserved on a horizon, then we must ask what happens at the most universal horizon of all, the one created by the accelerating expansion of our cosmos. This holographic view of reality does not merely rewrite the laws of physics, it shatters our most fundamental sense of place. The universe you perceive, with its vast three-dimensional depth, may be a magnificent illusion, a projection from a distant two-dimensional surface. This is the holographic principle, a concept born from the fiery logic of black holes. It began with a startling realization about information. As matter falls into a black hole, the information it contains, every detail of its atomic structure, seems to vanish, creating the infamous information paradox. But physicists Gerard T. Hooft and Leonard Susskind proposed a radical way out. What if that information is not lost? What if it is perfectly encoded, pixel by pixel, on the black hole's event horizon, the very boundary we see as its shadow? The entire three-dimensional volume of the black hole and everything within it could be described by information painted onto its two-dimensional surface. It is exactly like a security hologram on your credit card, where a flat, etched surface creates the stunning illusion of a three-dimensional image floating in space. Your experience of depth and solidity is a projection. Susskind himself stated the implication with breathtaking clarity: the three-dimensional world is an illusion. If this principle holds for black holes, could it be true for the entire cosmos? Our reality, with its galaxies, stars, and planets, might be a cosmic projection from a vast, distant shell that contains the universe. This idea finds a natural home in string theory, where certain mathematical descriptions of a volume of space without gravity are perfectly equivalent to descriptions of its lower dimensional boundary where gravity exists. The three-dimensional world we live in, with its force of gravity, could be a holographic projection from a two-dimensional world where gravity does not exist at all. This overturns everything we assume about locality, the idea that objects can only be influenced by their immediate surroundings. In a holographic universe, what happens at the boundary instantly affects the entire volume, suggesting that locality is not fundamental, but an emergent property that arises from a deeper, interconnected quantum system. How could we ever test such a mind-bending concept? Scientists are looking for signatures in the faint afterglow of the Big Bang, searching for patterns in the cosmic microwave background that might reveal a pixelated, holographic nature to spacetime itself. Others are using quantum entanglement, the very spookiness that hints at deep connections, as a tool to probe this idea. If the fabric of space is woven from quantum entanglement, then the holographic principle might be the loom. This is not just philosophy, it is a concrete, mathematical framework that forces us to question the nature of dimensionality itself. Are the three spatial dimensions we move through simply a convenient, emergent description for a reality that is fundamentally more flat, more information-based? This radical view of a projected cosmos inevitably leads us to a deeper question. If our universe is a hologram, who or what set up the projector? What are the fundamental settings, the precise constants, that allow such an intricate illusion to exist at all? Those fundamental settings for our cosmic projector appear to be impossibly perfect. The universe operates on a set of unchangeable numbers, the fundamental constants of physics, that seem precisely dialed for existence. If the force of gravity were even slightly stronger, the universe would have collapsed back on itself in a fiery big crunch long before stars could form. If it were marginally weaker, matter would never have clumped together into galaxies and stars at all. The cosmic expansion rate, the strength of the nuclear forces, the mass of the electron, each one is a knob on the universal control panel that is set to an exquisitely specific value. A little more or a little less, and the entire cosmic experiment fails. Consider the formation of carbon, the very element of life. Inside stars, 3 helium nuclei must collide to form a carbon nucleus. This process relies on a stunningly precise resonance, a perfect energy match that allows carbon to form efficiently. If the strong nuclear force were just a fraction of a percent different, this resonance would vanish, and the universe would contain virtually no carbon, no oxygen, and no life as we know it. This is not a single lucky break. It is a chain of cosmic coincidences so improbable it defies belief. As the renowned astronomer Martin Rees explored, just 6 numbers rule the entire universe, and the slightest deviation in any one of them would render the cosmos sterile and dark. So why is the universe so hospitable? One compelling answer is the anthropic principle, a simple yet profound idea. We observe these specific constants for one straightforward reason. They are the only ones that allow for observers like us to exist. In a universe where the constants were hostile to life, there would be no one to ask the question, but this leads to an even grander possibility. Perhaps our universe is not alone. The multiverse theory suggests that our cosmos is just one bubble in an infinite froth of universes, each with its own random set of physical constants. In this vast cosmic landscape, most universes are stillborn or barren. We simply find ourselves in one of the rare, lucky ones where the numbers lined up just right. This idea transforms the question of fine-tuning from a mystery of design into a statistical inevitability. Discoveries at the frontiers of particle physics and cosmology continually test this delicate balance, measuring constants with ever greater precision to see if they are truly constant or if they might subtly change over billions of years. This razor's edge we walk on between a chaotic void and a structured cosmos forces us to confront the ultimate nature of reality. Are the laws of physics a unique, elegant solution, or are we just the winners of an unimaginable cosmic lottery? That razor's edge of finely tuned constants may not be so fixed after all. The very rules of the game, the fundamental numbers we rely on to describe reality, might be changing. One of the most startling possibilities is that the fine structure constant, a number that dictates the strength of the electromagnetic force, is not a true constant. This single value, approximately 1/137th, governs how light and matter interact. It controls the energy levels of atoms, the color of the stars, and the very chemistry of life. If it were even slightly different, the universe would be unrecognizable. Yet, evidence is mounting that this cornerstone of physics might be shifting over cosmic time or across vast stretches of space. Astronomer John Webb and his team made a profound claim after analyzing the light from distant quasars. These brilliant beacons shine through ancient clouds of gas, and the atoms in those clouds absorb specific wavelengths of light, leaving a unique fingerprint in the quasar's spectrum. By studying these absorption lines, Webb's group found a slight but persistent anomaly. The pattern suggested that billions of years ago, in certain directions of the sky, the fine structure constant was minutely smaller than it is today. The shift is tiny, just a few parts in a million, but its implications are seismic. If confirmed, it would mean the laws of physics are not eternal and universal. They could evolve. The strength of electromagnetism, one of the 4 fundamental forces, might have been different in the past, or it might vary from one region of the cosmos to another. This idea is so revolutionary that the scientific community remains deeply divided. Other teams have performed similar analyses with conflicting results. Some see no variation at all, while others see hints in different directions. As Webb himself has emphasized with cautious humility, we desperately need more data. The hunt is now on with next-generation telescopes like the Extremely Large Telescope, which will peer deeper into the past with unparalleled precision. On Earth, physicists are using the most precise machines ever built, atomic clocks, to test for changes in the present. These clocks are so stable they would not lose a second in billions of years. By comparing different types of atomic clocks over time, scientists can hunt for any drift in the fundamental constants that govern their ticking. A confirmed variation would be more than a new discovery. It would be a complete rewriting of our theoretical framework. It could point toward the existence of new, unseen fields permeating the cosmos, fields whose slow evolution subtly alters the constants we measure. Some theories even suggest that such a changing field could be the mysterious dark energy itself, its relentless push driven by a fundamental constant slowly shifting its value. This possibility brings our journey through 25 discoveries to a profound close. We have seen space-time ripple, the universe accelerate, and matter emerge from a primordial asymmetry. We have glimpsed black hole shadows and questioned the nature of information. Each revelation shattered a piece of our classical intuition, showing that reality is far stranger and more interconnected than we ever dreamed. The potential that the laws themselves are in flux is the ultimate reminder that our understanding is not final. The cosmos is not a static kingdom governed by immutable decrees. It is a living, evolving system, and we are privileged witnesses to its endless, unfolding mystery. These threads of discovery, from gravitational waves to cosmic acceleration, were not spun in isolation. They form a single, intricate tapestry, woven over a century of collective human curiosity. The grand loom for this tapestry was built in the early 20th century with two revolutionary frameworks, Einstein's general relativity and the strange rules of quantum mechanics. These were the new languages for describing reality, but for decades they were like unplayed symphonies, beautiful theories waiting for instruments powerful enough to hear their music. The technological crescendo that followed gave us those instruments, giant radio telescopes that listen to the whispers of the cosmic microwave background, space probes that taste the solar wind, and continent-spanning observatories like LIGO and the Event Horizon Telescope that sense the faintest ripples in spacetime and photograph the unseeable. These are not the tools of a single nation, but of a species. The first image of a black hole's shadow was captured by a virtual telescope the size of Earth, a network of dishes from the high deserts of Chile to the frozen peaks of Hawaii, all synchronized by atomic clocks and the shared purpose of thousands of scientists across the globe. This collaborative spirit is the engine of modern physics, yet every single thread in this tapestry was once dismissed as impossible. Black holes were considered a mathematical fantasy for decades, an absurd overreach of Einstein's equations. The notion of an accelerating universe was so shocking that the teams who found the evidence spent years checking and rechecking their data, convinced they had made a mistake. This pattern of radical skepticism followed by reluctant acceptance is the heartbeat of scientific progress. It is a self-correcting process, a conversation across generations where each new discovery builds upon, and sometimes shatters, the foundations of the last. Solving the mystery of the solar neutrino problem did not bring closure. It opened the door to the profound realization that neutrinos have mass, forcing us to rewrite the standard model of particle physics. Finding the cosmic microwave background confirmed the Big Bang, but its perfect uniformity immediately pointed us toward the even more radical idea of cosmic inflation. This is the beautiful, unending cycle of exploration, where each answer unravels to reveal a dozen new, more fundamental questions. To see these 25 discoveries as a connected web is to understand that we are in the middle of a story, not at its end. The quest to decode the universe is a cumulative human endeavor driven by the tools we build, the collaborations we forge, and the courage to question everything we think we know. These 25 threads of discovery weave a single, stunning tapestry, from hearing space-time ring with gravitational waves to watching galaxies flee on a dark energy tide. Each revelation has forced the rulebook of physics to evolve. Our universe is far stranger, more dynamic, and more wonderfully bizarre than we ever dared to imagine. This relentless process of discovery echoes the wisdom of Albert Einstein himself, who noted that the important thing is not to stop questioning. Curiosity has always been our most powerful instrument, a tool that has consistently revealed a cosmos richer and more mysterious than our textbooks could contain. Every one of these cosmic truths, from the ghostly influence of dark matter to the quantum glow of black holes, reshapes our understanding of our own place in the grand scheme. We are not just living on a planet, we are participants in an unfolding cosmic story, one where the fundamental laws themselves may still be in flux. If this journey through the edges of physics has expanded your view of reality, there are countless more mysteries waiting for us. Let us know in the comments which discovery reshaped your perspective the most. Remember to look up at the night sky with fresh eyes, for the universe is not a finished book, but a story still being written, with its next